I wanted to expand on this a little bit from last time, and so maybe I'll take a quick picture of this. Just to remind ourselves that we did talk about it last time. And what I was going towards is that the idea that this thing, this property of the gradient is going to allow us to take a look at a function of three variables, function of x, y, and z, and be able to find the tangent plane. And so I meant to dig out some problems that are similar to this, but I forgot. Maybe I can find a problem. Nope. Maybe we'll just make one up. Well, let's see if I can find another problem here. This would be 14.5. What's directional derivatives and gradients? Is that like 14.6? All right, here's one over here. We'll take a look at this problem. Number 12, I guess. Oh, I have the answers here already. So what we have here is a something. It looks like it might be an ellipsoid, and we have a point that's supposed to be on this ellipsoid, and this ellipsoid is centered somewhere else. And if you notice, this is an equation. It's not a function defined as something. But what we're going to do is we're going to, and this clearly lives in 3 dimensions. So if I were to graph this, 2 parentheses x minus 8 squared plus y minus 4 squared plus z minus 5 squared equals 10. So if I take a look at this, zoom out far enough, it's a surface that lives in 3 dimensions, right? So this clearly is an equation of a surface that would be living in 3 dimensions. And hopefully that point will actually, if I were to graph that point as well, 9, 6, and 7, it's hard to see, but it should be on that. That point looks as big as almost as big as a thing. So I guess if we adjust this, this is in the positive, this is in the first octant, Let's call this 0. There we go. Well, it's there somewhere. So that point is actually on the surface. So the first thing to note that this is a surface. What we're going to do, though, is we're going to take this another dimension, and we're not going to see, and we're going to pretend that this is a function of 3 variables. So let f be a function of 3 variables from R3 to R, and then we'll define f of x, y, z to be equal to this whole thing. And notice I didn't put is equal to 10 because right now I'm looking at it as a function. So without the equals to 10, then this is some 4-dimensional object that we can't visualize. But the moment that I say that this is equal to 10, I want to rewrite the whole thing over again. But the moment that I say that this is equal to 10, now it becomes a surface. So let's make the distinction here that this is a function in 4D, and this is a level set of f, and the word set here we can replace with the word surface because the domain is 3-dimensional, and so we're looking at a 3-dimensional surface. So remember yesterday in our discussion, the set could be a curve, or it could be a surface, or it could be something even more weird in higher dimensions, depending on the domain. And if your domain is 2-dimensional, then you're looking at a curve. If your domain is 3-dimensional, then you're looking at a surface. So this is a level surface, and we've actually seen it in our graphing program that it actually is a surface. Okay? Yeah?
So that's the distinction. So is this both in 4 dimensions?
Well, no, this is in 3D because this is a surface, right?
Right.
So
it's not equal to just some function in 3 dimensions, and we don't have a fourth.
So you're pretend that this is W, and then W is your 4th variable. Okay? All right, now according to the theory, our gradient should be perpendicular to a level set. So let me rephrase that. Our gradient should be perpendicular to this level surface. So if we do a gradient, so I'm not going to put x, y, z there. Just say gradient is equal to, now let's take the derivative of each of these things with respect to x and with respect to y and with respect to z. So I think this is going to be 4 times the inside to the first power times the derivative of the inside. Or you can FOIL it out and then take the derivative. However you want to do the derivative. This is going to be 2y minus 4 and 2z minus 5. So saying that this is perpendicular to the surface isn't quite accurate, because what you have to do is you have to evaluate it at a particular point. Because right now this is a general gradient function. This is a function of x, y, and z that has x, y's, and z's in it. And the idea that this is perpendicular, like I said, is not quite accurate until you actually put in the value. So if we take our value and put 9 in for x, 6 in for y, and 7 in for z, then we're going to get a vector that's going to be perpendicular to the surface exactly at that point. So if we put 9 in for x, and we'll put 6 in for y, and then we'll put 7 in for z. Oh, is that right? 4, 4, 4? Yeah. Then that's our vector, and that vector is perpendicular to the surface. Okay? Let's see that in the graph. And for me to do this, I want my vector to start at that point and then going in the direction of the vector with a point added to it. So I don't know if you guys have been paying attention to how I use this. But if we take a look at this, and this is what do you call it? Its aspect ratio is a normal aspect ratio, 1 to 1 to 1. So it's not. Sometimes if you change the aspect ratio of this and you make you stretch along the x, then it doesn't look like it's perpendicular anymore. But over here, aspect ratio looks like it's going to make it look perpendicular. And so this is it's normal, right? So if I wanted to find the equation of the tangent plane, well, I have a point and a normal vector, so that's as good as done, right? So let's find the equation of the tangent plane. Using the gradient. So we're essentially using the gradient. And what do we know? That this is normal. And then we need a point. And our point is, what is it? 967 or something. And then we just put that together. So it'll be 4x plus 4y plus 4z is equal to, I suppose I could have just used 1, 1, 1, right? Because that's the same direction. But I used 4, too late. So 4 times 9 is, I don't know, plus 4 times 6 plus 4 times 7. The whole thing? And we could factor out a 4. No. Really? Because I was going to factor out a 4 out of everything. And this will give me an x plus y plus z is equal to, if I factor out a 4, it's just 9 plus 6 plus 7, which is, oh, it is 88. Sorry, I doubted you. Well, I'm not going to put 88 there because it's now 22. This was 88. All right, so if I graph this, I should see the plane that's actually tangent. Oh, this is graph calculator program. x plus y plus z is equal to 22. And we can see that this actually now is tangent to the surface at that point, and it's got a normal vector, and everything looks nice and neat. Okay? So let's summarize this into a formula. Usually we work with formulas first, and then we summarize it. Or we do an example. This time we did an example first, so now let's try to summarize this with a formula. Let's see if we can get a good picture here. That looks like it's a good picture. So this is our surface. I think I need to go back to darker purple here. What is it? 2x minus, what is it, 5 something? X minus 8, 4, and 5. X minus 8 squared plus y minus 4 and 5. So that's the surface. We have the point that was given to us. This point is 9, 6, 7. We found a vector. This is your gradient, which also happens to be your normal vector. And then we found our tangent plane. And those are all the components for this problem that we just did. Okay? All right, now the wrap-up, or the summary, is that if f, I'm going to use capital F, is a function from R3 to R with the point ABC or X naught, Y naught, Z naught. We've been using ABC. Let's use ABC. Then equation for plane tangent to f of x, y, z equal to some constant at the point ABC is given by so it's basically capital Fx evaluated at ABC. So this is the first component of your gradient, and then I have x minus a plus second component of the gradient ABC times y minus b plus fz ABC z minus c is equal to 0. Okay, if you peel this apart into pieces, you'll see that this is actually the gradient. Dotted with XYZ equal to, and then all those, the ones with a negative sign can go to the other side. It's actually the gradient dotted with a point, which is what we did in the previous example. Yeah? This is our variables for the equation. So when we need to create an equation of a line or a plane, we have variables x, y, and z. Okay? Oh, there's more. Yeah. Yeah. Oh, wait, there's more. Any questions so far? I mean, there's probably a lot of questions, but anything you can formulate in your head right now and ask? Yeah.
So those are just the fx, fy, and fc evaluated at those points are what we've been doing for a while now. We just take the derivatives and then just plug in the points.
Yep. Yeah. And if you want to relate this back to the previous problem we just did in the previous page, this is our, we found the gradient vector, and then we evaluated at 9, 6, 7. We got 4, 4, 4. And then we dotted this one with 9, 6, 7. That was the point, right? And then we dotted this one with x, y, z. That's the variable. And then this equation is exactly this thing. Okay, it's 4, 4, 4 dotted with x, y, z, 4, 4, 4 dotted with 9, 6, 7. Okay? All right, now. You guys ready for this one? This is kind of exciting. So, z is equal to f of xy is also a surface. My bet. So let's take a look at this little magic trick. F of x, y minus z is equal to 0. That makes sense, right? That wasn't a trick, silly rabbit. What if we considered this as a function f of x, y, z? Now, if I stop there, then I have now defined a function in a higher dimension. But if I say that this was equal to 0, what do I have? A level surface, which is a surface. And it's exactly the same thing. Right? With me so far? Now let's take the gradient. Oh, clever. I should have brought it to the other side. I was going to bring it to the other side. What do you think? All right, I'll leave it like this. Oh. Okay, can I switch it around? Sorry. Are you guys taking notes and pen? What I wanted to do was say z minus fxy. All right, so it's a level surface. Oh wait, maybe I should have had you guys think about what the equation of a tangent plane for this is. Yeah, let's do that for a minute. Equation of tan plane at the point AB. See if it'll fit in this box. Have to write small. Do you remember what it was? It was like z is equal to all right. It didn't quite fit. Yes, it did. It fit. All right. So that's our equation of the tangent line. All right. So this is our little preview. Now let's bring this to what we're talking about with level surfaces of functions of 4 variables, or functions of 3 variables, which is in 4 dimensions. But now if I set this equal to 0, we're back to this discussion about this being a level surface. So we have a level surface, and I'm interested in finding the equation of the tangent plane of this level surface. So if you remember, the normal vector is essentially the gradient of f. So what I want to do is I want to take a look at this generic function and take the derivative of this thing with respect to x, and then with respect to y, and then with respect to z. What is the derivative of this thing with respect to x? What's the derivative of z with respect to x? 0, right? So what's the derivative of this function with respect to x? That's just fx, right? Oh, except there's a negative sign. And then the derivative with respect to y, again, z is a constant, so this is just fy, oh yeah, and with a negative sign. And what's the derivative with respect to z? So derivative of z with respect to z is 1 minus, wait, there's no z's in here, right? F of x, y is just a function of x and y, so those are the only 2 variables in there, so there's no z. So that's just 0. Now, if you look back, how far do we look back? 2 weeks ago. Partial derivative, tangent planes. Oh, I think it's the following week. So it was just last week that we just talked about it? Here it goes, right here. Bam! Same thing, right? Normal vector. So this notes from 10.6, we saw that we got the normal vector and it's the exact same thing. But this time we've approached it as if we sent it back to the fourth dimension as a level surface. So if we follow through the rest of this, we should get the same result, right? So according to the formula that we just came up with, we need a point AB is just a two-dimensional point, but if this is in 3 dimensions, we need to put that third point, third value in there. So in 3D, we have the point A, B, and instead of C, it'll be f of AB. So if we go through the process, we would have fx, we'll put negative if you want, x minus a minus fy, y minus b minus, well, that would be a plus 1, z minus c equals 0. And then if you shuffle this around, you can make it look just like this. Say if you want to solve for z, you bring this f of a over to the other side, you bring these two negative terms to the other side that become positive, and then you would get your tangent plane. Okay? So it's the same thing. Now, you didn't need that for today's quiz because today's quiz dealt with you having to come up with this formula, or trying to remember that formula, or something similar to that to find the equation of the tangent plane. But now we have the power to do this in a function of 2 variables or a function of 3 variables. Okay? Pretty cool, huh? I think it's cool. All right, we're going to shift gears again and do something that we were doing yesterday, which is still talking about max and mins. But we're going to do it a little bit differently. And we're going to focus on, you know how last time we focused on finding the max and mins by finding the extreme values. We found the critical points, and then we checked the boundary. So today we're going to focus just on the boundary. If you saw, that wasn't very easy, the example that we did. Did we finish that example, by the way? Last time? Or did I just say forget it? All right, whatever. So let's find extreme values on boundaries, or sometimes they call them constraints. And for us to study this, we're going to use this thing called Lagrange multipliers. Yeah. Yeah, now we're 14.8. Not labeling my stuff correctly. Thanks. All right. So let's start with a really simple example. Let's maximize a function, and let's just say x plus y. That's a pretty simple function. Given a constraint x squared plus y squared equals 1. So what you have to do is you have to be given a function that you're maximizing, and a constraint is a relationship between the two variables in the domain that's going to say that your function has to be within this constraint. Okay, we've done something similar to this, similar to this, where we're maximizing an area or something like that, and maybe we'll do that. Maybe that's what we should do. I'm already doing this. We'll do the area problem later. So the idea is to try to figure out how to maximize this, how to find out the values as long as your x's and y's satisfy this equation. Actually, I want to go back to the... Can I change the problem? Sorry, I need to change the problem. Don't you hate it when teachers do that? They just take their eraser and wipe everything out. Especially if you're trying to take notes in pen and you're using color pen just to be all neat and stuff. So yeah. X times y, yeah. Looks like a dot. Well, it is a dot, but it's not the dot product because these are scalars. Okay, so the reason why I wanted to change this because I wanted it to relate to something that you've done before, and back in calc, everybody's done this problem. So you can imagine that this is x is the length and y is the width of a rectangle. You're trying to maximize the rectangle based on the amount of fence that you have, and so your fence is restricted to like 10 meters or something. And so you got the perimeter 2x plus 2y is equal to 10. That's like that problem. And we're able to do that problem back in Calc 1 because we can do some simple substitution here so that we can have a function of one variable and just take derivatives and stuff. But I want to show you that we can also do this in 2 dimensions since we have 2 variables, x and y. And we can do this by using the method of what's called Lagrange multipliers. But before we do that, let's examine how this might look like on a surface. Did that sound like a question? That was a rhetorical question. I think I know what I'm doing. I hope I know what I'm doing. Sometimes I don't know what I'm doing. So this is what we have. And if we zoom out enough, we'll see the plane. And we're trying to maximize something. So we're trying to maximize the purple graph. Let's make it blue. And let's make it, well, that's not blue. Let's make it transparent. Let's make both of these transparent. So what we're doing is we're essentially finding, more or less, we're finding where they intersect. And where they intersect, wherever they intersect, we want to find the highest point, right? Because that's the idea of maximizing. So looking at this in 3 dimensions could be a little bit difficult. So what we're going to do is we're going to look at this in 2 dimensions. What? How can we look at it in 2 dimensions? It's kind of weird. Let's see. What? Yeah, how about that? How about we do a level curve? Let's see if I can do some magic here. To x prime. Wait, does level curve? Well, this is kind of already a level curve, right? So let's take a look at level curves of this. X squared plus y, x squared times y squared is equal to 0. Yeah, that's weird. Let's do 1. Can you guys see? Let's do 2. Let's do 4. Level curves, right, are just setting that function and then setting it equal to a constant, right? So my function is x, y, and I'm just setting it equal to a constant, and then I'm seeing how it looks like in the graph. Let's do 18. 6, maybe. And then 8. All right. Now let's think about this. Let's maybe stop this from spinning. So this purple plane is a cutting plane where the intersection of that plane and the surface, the wavy surface, let's make this plane yellow. The intersection of that plane and the blue surface is going to be these curves. So if we keep moving up, we'll see that it'll change according to that, right? So actually, let's make it even look nicer. You can't even see it. Maybe if we can get a nice color, like green, purple. Purple's a nice color. You see it moving around? All right, now let me adjust this so that we're looking at the top of the intersection here. There's a good view right here. That's where I want the intersection. Now let's look at that plane. Right around there. So what can you say about that point that we're looking at? Yeah.
It gets closer and closer to the, as we move the plane upwards, it gets closer and closer to the level curve that we created.
So closer to the level curve, what does that mean? What do you mean closer to the level curve? What is the level curve doing with the constraint curve? The constraint curve is that red line. The level curve are these hyperbolas. Is it? They're touching. Remember what happens when two curves touch? What are they called? No. I mean, they're intersecting. They're kissing. Remember that? We have kissing curves. No, you don't remember that. But what did you say? Nosculating? No. Somebody said it. What, did you say something? Tangent. Star-crossed lovers. Oh, tangent. They're tangent. They're like tangent. Or they have the same tangent line. Now, if they have the same tangent line, they must also have the same. Finish my sentence. If they have the same tangent line, they must also have the same tangent vector, slope. Some more? We're not talking about planes here yet. Same normal. Same perpendicular. Or maybe they're not exactly the same normal vector, but their normal vector should certainly be a same direction or at least collinear. Okay? So, with that visual in mind, and with that, without proving it really, the gradient vectors, oh wait, this isn't really a function, but we can sure make it a function because we just did that earlier. We have f of xy equals x times y. We have, let's call this g of xy is equal to 2x plus 2y. We could say equal to 10, but we'll use that later on. But the gradients are normal vectors, are vectors that are normal perpendicular to these curves. And the gradients, because they're normal vectors, we say that we want to look for these things when they are collinear. And one of the ways to describe something that's collinear is to say that one vector is a scalar multiple of the other. And so we're going to put a scalar next to one of these. It really doesn't matter which one. And the scalar that people use for these things is called lambda. It's a Greek letter L. And this is the equation that we use for Lagrange multipliers. L for Lagrange. Okay? Lambda is the Lagrange multiplier. That is a scalar that says that one gradient is a scalar multiple of the other. Okay? Now that's a simple, innocent-looking equation that would normally yield to some really difficult algebra. Now this first problem I don't think is that difficult, but let's see. Should we do it? I'm asking because it's already past time. But you said go for it, so let's go for it. So derivative with respect to x and the derivative with respect to y. And then the g is just 2 and 2 because they're constants. And so we set them equal to each other, Lagrange style. And so what are we going to come up with? We're going to come up with y is equal to 2 lambda, x is equal to 2 lambda. We have 2 equations and 3 unknowns. 2 equations and 3 unknowns is not really going to help us solve for this because we have 3 unknowns. So we need a third equation. Guess where the third equation is coming from? The constraint. All right? And how you solve for these things is going to be up to you, and like I said, could be really algebraically difficult, but there could be some tricks that are hiding somewhere. Oh, and one more thing. You want to look for x and y. If you find lambda, great. If you don't, who cares? Because you're not going to use lambda. You're just going to use it and leave it. Lambda stands for love them and leave them. No, I didn't want to say that. Okay, I'm starting to lose my mind here. So for me, maybe if I can just solve for lambda, yeah, we can do a bunch of substitutions. So we got 4 lambda plus 4 lambda is equal to 10. Lambda is equal to 5/4. Now again, you don't need lambda, but in this case we happen to have found lambda. Great, it's fine. But more importantly, we want x and y. So x is equal to 2 times 5/4, which is 5/2, and y similarly is 5/2. Okay? So if we put that into the original function, we're going to get 25/4. Now, one more thing. Let's look at our graphic. The level curves, we're just kind of randomly choosing them, right? If we put 25/4, we're going to get the exact value or the exact level curve that we were looking for. So on the three-dimensional graph, you'll see it's at the tip. On this level curve graph, you see that they're kissing. All right. I have a handful of, I'm going to put this online, unless you want to take a picture of it now, but I found some neat problems that I think are kind of cool that would be extra credit, 1 point each. Now, each problem is going to be a bunch of steps and kind of a lot of work to do. And so I'm giving 0, 1/2, and 1 point for depending on how much you do on each of these problems. And whatever you turn in on Monday and whatever I grade will be extra credit points for the next test. Okay, and I'll post this up online. Oh, another thing is I'll post it up online too. The problem that we did, I have I wrote it all out step by step, so you can take a look at that as well. Have a good weekend. Study for this class. It's getting harder.
Can you explain stuff about the makeup exam for the